This unit deals primarily with what are called trigonometric identities and trigonometric equations. We've already studied how to solve trigonometric equations, either linear trigonometric equations, which I've called basic, or quadratic trigonometric equations, which I've called complex. But there are these things called identities, and we're not going to get into identities today, but as a preamble to the unit, I think it's pretty clear what I'm saying up here. Sine gerene over cos gerene is tan gerene, and what I'm telling you is that if you take a particular angle, any angle you want, whether it's in degrees or radians, and you take the sine of that angle and divide by the cosine of that angle, you will get the same thing as the tangent of that angle. And a couple of people were talking before class about why that's the case. Well, you can use the unit circle, and you know that on the unit circle, sine of an angle is the y-coordinate, and cos of the angle is the x-coordinate, and tangent of an angle is the y over the x-coordinate. In other words, this thing which we call an identity, we wouldn't write gerene. We'd say sine of theta over cos of theta equals tangent of theta. This thing which we call an identity happens to be an identity because we've defined tangent to be that way. Similarly, sine squared of theta plus cos squared of theta will always give you 1. The bulk of this unit deals with equations and identities. This might as well say trigonometric identities. There are reciprocal identities, quotient identities, Pythagorean identities, sum identities, difference identities, double angle identities. There are all these identities that we're going to be working with. And if you were to look at your formula sheet, that whole right side of your formula sheet is just blanketed with trigonometry, right? Everything that's on there that we haven't talked about are identities. Some of the things we've talked about are identities. Cosecant theta equals 1 over sine of theta is an identity. I probably didn't call it that before, but it's an identity. We're going to be proving trigonometric identities. We're going to be using identities to solve trigonometric equations. So that's where the practice is going to come in this unit. In the meantime, we've split up in this high school all of the 3 chapters on trigonometry partway through chapter 5. So the last unit dealt with all of chapter 4 and a couple of sections in chapter 5. Today what we're going to do is look at 5.3, which is the tangent function, and 5.4, which is how to solve trigonometric equations graphically. We're going to be looking at analyzing to begin with the graph of y equals tan of x. You already know what y equals cos of x looks like. I hope you do, because you wrote an exam yesterday that would have included that in some fashion. And you already know what y equals tan of x looks like, right? They are periodic functions that oscillate up and down. Well, we haven't talked about tangent of x, so we're going to start with that. There's very little you need to know about it, but we do have to cover it. And then we're going to get into solving trig equations graphically. So this is what y equals tan of x looks like. If you were to take your graphing calculator and just go y equals tan of x, and although it doesn't really matter what mode you're in, let's go in degree mode, just so that we're all on the same page. And then go zoom trig, which is zoom 7. You get this shape. And I've decided occasionally to not put arrows on graphs in print documents that I would like to put, because Alberta Learning has stopped putting arrows on the ends of graphs. These blue lines on the screen continue up and down forever. They don't just end or begin in these positions. So there is an extension of all of these curves going up. One last thing here before I get to this graph in detail. If you go to your window settings, when you go zoom trig, and I don't know why the TI family of calculators does this, it doesn't go from negative 360 to 360. So if you want to see an identical image to kind of what I'm looking at on your note package, then we can change this to negative 360 and this to 360. And I hope you understand that 360 is 2 pi. So we're looking at the same graph. If we want to really look at the same graph, I suppose we should go from -8 to 8 for y, although it's not necessary. But if we want to, we can. And my main point here is that if you ever want to see what y equals tan of theta or y equals tan of x looks like, use your graphing calculator if you forget. Now, there are breaks in the graph. In Math 20-1, you encounter these dotted lines for certain functions. This is called a vertical asymptote. One of the funniest words in mathematics. And there are all these vertical asymptotes because there are places where you are not allowed to take the tangent of a rotation angle. This vertical asymptote here is at pi over 2, or 90 degrees. Now, why does the graph not exist there? That's what that vertical asymptote means. Well, it doesn't exist there because you can't take the tangent of pi over 2. Pi over 2 is 90 degrees, or on the unit circle, it's at the top of the rotation around the circle. And tangent is always y divided by x. But the x-coordinate at pi over 2 on the unit circle is 0. Don't confuse the x-coordinate that I'm talking about, which is 0 on the unit circle at pi over 2. Don't confuse that with the x on this graph. The x on this graph is actually theta. It's actually the rotation that takes you to a particular location. But regardless, when you look at a rotation of pi over 2 on the unit circle, the x-coordinate at that location is 0. So you're left with the y-coordinate, which is 1 over 0. That's how we find tangent. Well, you can't divide by 0. And that happens again at 3 pi over 2. So what happens is, think about this. Tangent is y over x. At 0 degrees, y is 0 and x is 1 on the unit circle. When you divide 0 by 1, you get nothing. As this rotation goes up, the y-coordinate gets bigger and the x-coordinate gets smaller. So if you were to look at a very large angle that's very, very close to 90 degrees, you have a y-coordinate that's really close to 1 and an x-coordinate that's almost 0. So you're taking a y-coordinate and dividing by a little tiny, tiny number, and the result is tangent starts to explode. It takes off. It gets bigger and bigger and bigger. For example, and I'm in degree mode, so I'm going to take the tangent of 2 degrees. Well, I get a very tiny number because at 2 degrees, y is still very, very small and x is almost 1. So you have a very small y over x. If I take the tangent of 89.9 degrees, I get 573 approximately. Because at 89.9 degrees, the y-coordinate's almost 1, and the x-coordinate is really, really tiny. When you have a fraction and the bottom gets really small, the whole fraction explodes. So that's why all of these curves continue up. And we would describe, and we're going to use this language later on in the course, we would describe these curves as being asymptotic against those vertical lines. And what that means is the curve will always, always get closer and closer and closer to that line. There's no limit to how close it can get to that line, except that it can't touch it. And at the same time, it will go up and down to positive and negative infinity. I hope you understand that this continues outside of the grid we're looking at in both directions, right? So, first of all, there's no amplitude here. The concept of an amplitude makes no sense. This is not a sinusoidal graph. Let's answer some questions about it. What is the domain? Well, we've already established that there are certain values of theta, if we want to talk about a rotation angle, that you cannot take the tangent of. And on this graph, remember, x on this graph is the rotation angle you're taking the tangent of. So x cannot be equal to pi over 2. right? You cannot take the tangent of 90 degrees. And you cannot take the tangent of 3 pi over 2. So if you look up here at me, on the unit circle, you cannot take the tangent of any rotation angle that lands at the top or at the bottom. Well, these two positions, angularly speaking, are pi radians apart. So what we can say here is that x cannot be pi over 2 plus multiples of pi. When I say plus, I really mean plus or minus, and that plus or minus is accounted for by saying that n is an integer. So when you go to pi over 2, or negative pi over 2, or negative 3 pi over 2, or positive 11 pi over 2, any multiple of pi added to pi over 2 will give you a mathematical slap on the hand, so to speak. What is the range? Well, the range is y is any real number. This graph extends forever in both directions. What's the period? This is really maybe the only thing you're going to be asked about on the diploma exam has to do with the period of tangent in a roundabout way. The period is not 2 pi. When you look at what happens to the graph, it repeats every pi. This and this are separated by pi radians, or 180 degrees if you want to work in degrees, if you want to answer questions in degrees. So the period is pi. It's not 2 pi. What that means, and this is occasionally what happens is the diploma exam will introduce something which is not actually part of the curriculum. And what they say is that students are not expected to be able to solve problems involving this function. You know how we talk about sine of bx and cos of bx and all that? What the curriculum says is you're just limited to knowing the features of this graph. But every now and then they ask you about the period of this graph. And I get why they can do that, because you are still expected to know about stretch factors. But the period of this graph is not 2 pi over b. The reason why the period of sine of theta and cos of theta is 2 pi over b, the reason why the period of cos of bx, or b theta, and sine of bx, or b theta, is 2 pi over b is because the regular period of sine and cosine is 2 pi. The regular period of tangent is merely pi, so the period of tan of bx, or tan of b theta, will be pi over b. And if you want to be, pedantic about it, if b happens to be negative, it's over the absolute value of b. What is the amplitude? Do you have the word amplitude in your handout? I think I've gotten rid of it. Right? Now what I used to do is leave it in, and then I would just do this. Because it just doesn't make sense, right? There's no amplitude. There's no distance from the middle vertically of the graph to the maximum, because the maximum is infinity. Equations of asymptotes. So this is a very subtle thing, but the language in mathematics is often subtle. These are the equations of the asymptotes, and the equations of the asymptotes are the locations of the vertical lines that the graph cannot be. So when you look at what I wrote for the equations of the asymptotes and what I wrote for the domain, they're not the same, but they have the same structure, right? The domain is telling us what x is not allowed to be. The asymptotes are telling us where those vertical lines are, which happen to be where x cannot have a value. X-intercepts, well, again, just follow my arm movements up here. We know that tangent is undefined here and here because y over x here and here will be 1 over 0 and negative 1 over 0. Tangent of x, or theta if you like, if it makes you sleep better at night, change all your x's to thetas in these equations. Tangent of x, or tangent of theta, is 0 here and here, on the unit circle because tangent is y over x, and here y is 0 and x is 1, here y is 0 and x is negative 1. 0 over whatever is going to be 0, which means that the x-intercepts will be multiples of pi. And I'm not sure when I started doing this, but I've done it all day today, so I don't know if I've been doing it all semester. We would probably write n pi in this context, or you might see n pi instead of pi n, but that shouldn't bother you, should it? Okay. Are we okay with that? Okay. Y-intercept is 0. Because the tangent of 0 degrees or the tangent of 0 radians will give you every single time an output of 0. One quick example with this. This is maybe a type of question you might see on an exam. If the period of f of theta equals 5 sine r theta over 7 minus 9, if the period of that is the same as the period of tangent, then what is the value of r? Well, we know that this period is pi. Why do we know that? Because we just need to know it. And if you're stuck, you get the exam sweats and you're writing an exam, go y equals tan theta on your calculator, go zoom trig and figure out what the period is. It's 180 degrees or pi. What that means is that the period here is pi. But we also know the period of a sine function is 2 pi over b. And in this particular question, or function rather, b is r over 7. b is the parameter that you multiply the independent variable, x or theta, by. So what that means is that the period of pi has to be equal to 2 pi over b, which is r over 7. So we need to solve this. You know, there's another way to look at this, and I'll look at it this way in a second, because I think many of you already know what r is without writing this down, but we'll see. So the pi's cancel. I'm left with 1 equals 2 over r over 7. I would prefer to multiply top and bottom by 7. Top and bottom of that fraction to get 1 equals 14 over r, and then you can rearrange that in r as 14. I don't know, maybe I misread you, but how many of you understand that in order to go from a period of 2 pi for sine to a period of pi, b has to be 2? 2 pi over 2 would give you pi. What that means is r over 7 has to give you 2, so r has to be 14. There's a way to kind of reason it out, and I see a couple of you nodding, some of you not, some of you looking at me with a little bit of a glazed eyes, but that's okay. We can always do it using the rules. So period of this graph is always 2 pi over b for sine, and we're told the period is pi. So we found out the value of r using that. All right, now we're going to get into the most important aspect of this lesson, which is very important for what we're moving on to tomorrow. First off, a little bit of a review. Solve this trigonometric equation. I would describe this equation as being very simple. My standards have changed since we first learned about trigonometric equations. I would have called this a complex trigonometric equation because it's quadratic. But I think this is a very basic trigonometric equation to solve. You have to factor it. It has to be 2 cos x times cos x to give you the 2 cos squared of x. It needs to be a 1 and a 1 to give you a product of 1. I know that the product is not 1, it's negative 1, but the way I factor, I deal with that negative when the time comes. My outer is my outer is 2 cosine of x. My inner product when I FOIL is 1 cosine of x. And when I look up top, what I want for the sum of these is negative 1 cos x, which means the 2 cos x needs to be negative. And then I just trace this back to where it came from. It came from the outer product. That means this has to be negative and this has to be positive. Capiche? You're in agreement with that? And probably in the time it took for me to explain that, you would have factored it already. Maybe been able to factor 2 or 3 of these like this. This is just my scrap work. I won't erase it. I'll move it out of the way. So then what you do is you say that 2 cos x plus 1 is equal to 0. And you say cos x minus 1 is equal to 0. Some of you, when you wrote your exam, didn't show the equal 0. I would tell you that that's poor form. I don't believe I took off any marks for that, but a marker in Edmonton when you write your diploma exam might not be so kind. You really should put equal 0 for these. So we solve this. You end up rearranging this for cos of x and getting negative 1/2. You rearrange this for cos of x and you get 1. A serious mistake that you may not think is a big deal, but some of you on your exam were doing this. This is a serious, serious problem. That's like writing root. Root of what? Right? Cos is not a thing. Cos of x is a thing. So you want to watch out for that. I think I might have just been in a friendly mood when I marked and just wrote them in and not worried about it, but you really should do that. On your exam, and your exam was different, you had a reciprocal trig function, either secant or cosecant, depending on which exam you had. Many of you just kind of, as if by magic, said x is equal to 2 pi over 3 here, and x is equal to pi 0 or 2 pi. Are we going to include 2 pi? Let's take a look. Yep. So just think about this for a second. Just think about, we'll start with the easy one. Cos of x equals 1. So that's the x coordinate on the unit circle has to equal 1. I think for full marks, you have to say that, a minimum of say that, and also draw the unit circle and show that point. And I get that for some of you, this is a very easy journey. It's just in your head and you got it, right? But the purpose of a written response is not to demonstrate your superiority in math. It's to prove your superiority. It's to show the marker that you know what's going on. And that does not include an explanation of, I wrote. That's a description of what you did. An explanation is to say that I'm looking for a place on the unit circle where the x coordinate is 1, because on the unit circle, cosine of theta is the x coordinate. You don't have to write that much, but something. And then, I think if you're really on top of things, it's not unreasonable to say, if I saw this diagram here somewhere, there's more that needs to be done. But if I see that diagram, I know you know what's going on. Really, you should be putting was it negative 1/2? Yeah. Negative 1/2 comma root 3 over 2. And by the way, there's another one here I didn't put yet, 4 pi over 3. Nope. 2, 3, yeah, 4 pi over 3. You need to have these things. I mean, some of you did such a beautiful job of this. A couple of you pulled out highlighters. I'll move this down so you can see this. Pulled out highlighters and did something like that. That's going above and beyond. I don't think you need to do that, but you need some explanation. So from 0 to 2 pi, the solutions are 2 pi over 3, 4 pi over 3, 0 and 2 pi. Are we in agreement there? Okay, that's the last unit. What I want to talk about is solving this equation graphically. And I want to do this in two ways. One is to zero the function and graph y equals what the function is equal to, which is 0. In other words, we're going to graph y equals 2 cos squared of x minus cos of x minus 1. When you enter 2 cos squared of x, this is how you enter it. Now, I know, at least to me, that looks as though I'm squaring x, then taking the cosine of it. So for years and years, I would have told students, bracket cos x, n bracket squared. But you don't have to do that, okay? When you enter 2 cos of x, n bracket squared, that squared is not inside the brackets with the x, it's on the argument as a whole, the function as a whole. So it's going to square cos of x, and then minus cos of x, and then minus 1. Now, we are going to want answers in radian values, but we will not recognize radians in decimal form. So what we're going to do instead is make sure we are in degree mode, and then go zoom trig, keeping in mind that it goes from negative 352.5 to positive 352.5. Now, what are we interested in? We're interested in where this is 0. And what we have done is that, right? So we're interested in where y is 0. Well, that's called an x-intercept. When you zero a function, and this should not be the first time you've been exposed to this, although it is with trig, when you zero a function and graph the result, or zero an equation and graph the result, the x-intercepts of the graph will be the solutions to the equation. I'm going to adjust my window settings here, and I'm going to manually go in and go from 0 to 365. I just want to go a little past 360. And I should have pointed out before I got rid of that view, did you remember that most of the negative portion of the graph is not needed vertically? So I'm going to go from negative 1 to 4. And what I wanted to do is find the x-intercepts. And you can see there are 4 of them. So I go to my calculate menu and I choose 0. That's how we find an x-intercept. I scroll over to, now I kind of regret, it's okay. I was going to say I kind of regret going from negative 1 to 4 because I've kind of blocked out my view here. But I'm going to put the cursor there, enter, and go a little bit to the right of that and hit enter. And I get, your graph didn't look like mine, did it? I forgot to close the brackets on the argument of cos of x. I should have been, and I still did it. Well, that's going to change my window settings. Well, no, I guess it'll be okay. So let's find these x-intercepts here in the middle first. 0. Go to the left of it, hit enter. Go to the right, hit enter, and you get 120 degrees. Are you fine with me saying we could repeat that for the other x-intercepts? And get 0 degrees, 120 degrees, 240 degrees, and 360 degrees. And when you convert those into, I'll just put this up here. No, we'll do this. When you put those 0 degrees into radians, you get 0 radians. 120 degrees is 2 pi over 3. 240 is 4 pi over 3. And then 360 is 2 pi. You get the solutions. Are we okay with that? Okay, I don't like that. I don't like doing that. Okay. What I would do instead, if you look at the original equation, it's already equal to 0, but what I might do is this. And instead of saying I want to find or x-intercepts, I would say I'm going to plot this as y1 and this as y2. And I'm going to find out where they intersect. It just turns out it's easier to find a point of intersection on your calculator as opposed to x-intercepts. You have to worry less about window settings with this method. So if I do that, and I'm going to go back to zoom trig. Okay. Zoom trig. So here is 2 cos squared x minus cos x. And here comes positive 1. If I want to find a point of intersection, I go to my calculate menu and choose intersect. And all I have to do is just go anywhere near an x-intercept, and then hit enter 3 times. I don't need to worry about whether I'm left or right. Now this is a weird one because it's tangent to that point. I'm hoping it finds it. It may not though. No, it does. It's giving you a number that's so small, it's saying 0. But you should know it's 0. If I do the same thing over here, and if you're wondering how to go from moving on one function to moving on the other, you just toggle up and down. So I go over here, I'm going to get 120 degrees. And again, I don't have to scroll left and right and do all that weird stuff. I just have to be in the right vicinity and hit enter 3 times. That brings up a very interesting point, is that had I had this lesson before we wrote our exam yesterday, you should have been able to solve any multiple choice question that had an equation by doing this. Don't be mad at me. Thank me for teaching you how to do it properly, because if you can't, you're going to run into trouble. Okay? It's right now? Okay. So if I ask you to solve for x, you cannot do it algebraically. I'm telling you this right now. If you start to rearrange that for x, you will get an incomplete solution. It's not possible. It's not possible in this class. So we're going to solve this graphically, and this is a very important skill for tomorrow. So I'm going to put in for y1, 10, and for y2, I'm going to put in 6 cos pi over 4 bracket x plus 7 plus 8. So we put 10 in for y1, 6 cos pi over 4 bracket x plus 7 n bracket plus 8. And again, for those of you that have your calculator in what's called math print mode and you type, things go off the screen, you want to just scroll back and forth a couple times and make sure that you've entered it correctly. So bracket pi over 4, bracket again, x plus 7, close brackets plus 8. But here's the kicker. We want to find out where they intersect. So if you were to go zoom trig, oh, by the way, better put your calculator in radian mode, because I don't see a degree symbol there. If you go zoom trig, you don't see anything. Well, you see something, I suppose. Why don't you see anything? Well, this parameter of 6 is the A value, which is the amplitude, and D has a value of 8, which means the middle of the graph is up at 8, and it goes 6 above and 6 below. Okay, there's another issue. what we always want to look at is we want the graph to be something that includes the max, the min, and we want one period of the function, usually here. And the period may not be 2 pi. So we need to figure out what the maximum and the minimum y value is, and we need to figure out what the period is. Give this some thought and see if it makes sense to you that the maximum value of y is 14. Because the vertical displacement is 8. That's the middle of the graph vertically, and it goes 6 above that, so that's 14. And does it make sense to you that the minimum will be 2? So when we go to our window settings in a minute, we probably want to go from maybe 0 to 10. Okay. What about the period? Well, the period is 2 pi over b. And b is pi over 4. So we simplify that to get the period, and the period of this graph happens to be 8. A lot of ways you can get 8. My preferred method is to multiply top and bottom by 4. The pi's cancel, the 4's cancel, the period is 8. So this is 8, 16. 16. Okay, doesn't matter what the scale is. There's y equals 10, and here's the function for one complete period. And if you've done this right, since it's one period, you should get the intersections occurring twice. So all you have to do is find the points of intersection here. Intersect. One of the solutions is approximately 2.57 radians. The other solution I'm pretty sure you can hold this key down on your calculator. If I do it, my program thinks I want to right-click, so 7.43. Don't worry about the domain that's given here. I'm not interested in that. Okay? I'm interested for this question in the solutions from 0 to 1 period. If you do want all of the solutions from 0 to 2 pi, then you can take either of these and keep adding 8, because 8 is the period. But I don't care about that. In fact, if you want, just cross off the 0 to 2 pi. I'm not interested in that. All right, let's try another one. And again, I have to change my notes. I really don't care about that. I mean, I will do this one from 0 to 2 pi because the period is 2 pi anyway, but let's go ahead and graph this. I'm going to graph negative 300, and I'm also going to graph negative 520 sine x plus 12 n bracket minus 740. What do we want to do for the window settings? Well, since b here has a value of 1, the period of this function is 2 pi, so I'm just going to go for 2 pi. I always want to go one period. This is the skill I want you to get out of today's lesson. So in my window setting, I'm going to go from 0 to 2 pi. It doesn't matter what my scale is. And for y, well, I'm going to actually draw this for you. This is negative 740, and it goes up 520, and it goes down 520. Would you agree? So we need to add 520 to negative 740 and get Was that 220? Negative 220? And when we take away 520, we're down at negative 960, I think. Let me put these up here so you can see them. So this number up here will be, how's my subtraction, by the way? Can you just confirm that? Okay, and down here will be negative 1260, I believe. Okay. I would probably go negative 300 or 1300 rather. Up to, might go up to 300, negative 300. I definitely would change the scale. If you just leave the scale at 1, it's going to try to crowd in over 1,000 ones, 1,000 ticks. So double check everything. My window setting is good, I believe, negative 1,300 to negative 300. Pardon me, I guess negative 200, right? We need to go higher than negative 220. And double check for my functions, negative 300 and then negative 520, sine theta plus 12 minus 740, graph. So we'll find those two x-intercepts. .72 and do that again. I think I might have chosen 0 by mistake. 4.72 and 5.84. Are you getting the same numbers? Okay. Did I just see 5.84?